Today we're going to have a look at some of the uses of electrolysis. But before we go into that, we have to look at how the reaction will look if we use reactive electrodes instead of inert carbon electrodes. Now the setup would look the same as normal carbon electrode electrolysis. We'll have our beaker with our electrolyte. For this example, we're going to use aqueous copper sulfate. And then we have two electrodes. We still have one cathode and one anode, but these electrodes are made up of copper, which is a reactive metal. Our electrodes are then connected to our power source. Now our aqueous copper 2 sulfate will be able to dissociate into copper 2 plus ions and sulfate 2 minus ions. The copper in our electrolyte will move to our cathode, which is our negatively charged electrode, and it will cause copper to deposit here, meaning that our cathode would increase in mass. Now on our anode side, copper would be released from the anode into our solution, meaning that our anode decreases in mass. Now this happens because at the cathode, the copper ions are reduced, meaning that they gain 2 electrons and deposit onto the cathode. At our anode, the copper atoms are oxidized, meaning that they lose 2 electrons, becoming positively charged and will enter our electrolyte. This means that overall, the mass gained by the cathode is equal to the mass lost at the anode. It will also mean that the copper ions that are put into our electrolyte replaces the copper ions that are exiting our electrolyte and is deposited on our cathode. We can see this practically because the electrolyte will not lose its blue color like with electrolysis where carbon electrodes are used. This implies that the concentration of the copper 2 plus ions in the solution remains constant. Now let's look at some of the uses of electrolysis, and the first example that we're going to use is electroplating. Now electroplating is a process where the surface of one metal is coated with a layer of a different metal. Now the cathode or the negative electrode will be the object to be electroplated, and the anode, the positive electrode, is made from pure metal that will be plated onto the object. The electrolyte would be an aqueous solution of a soluble salt of the pure metal at the anode. Now as an example, we can use tin chloride electrolysis. So here our electrolyte is made up of tin chloride. We then have our anode, which is made up of tin, and we have our cathode that would be made up of iron. Now the tin ions in the electrolyte will move towards our cathode and will be deposited onto the iron electrode, covering it in tin. Now tin at our anode will then be deposited into our electrolyte, keeping the concentration of tin in our solution constant. Now we can see the half reaction of tin here at our anode, where tin loses 2 electrons to produce tin 2 plus ion. Then at our cathode, we can also see our half reaction, and this is where tin gains 2 electrons to produce solid tin onto our iron. Now electroplating is done to make metals more resistant to corrosion or damage, like for instance chromium and nickel plating. We can also use examples like galvanizing. So this is zinc plating or coating, and this is typically done to iron and steel to prevent rusting. Then of course, electroplating can also be done to improve the appearance of metals, like for instance coating cutlery or jewelry with silver. Now the second use of electrolysis is the use of hydrogen as fuel cells, and this is used as an example usually in cars. Now here, hydrogen and oxygen react to produce water that would release energy. Now a fuel cell is an electrochemical cell in which fuel donates electrons at one electrode and oxygen gains electron at the other electrode, meaning that hydrogen will produce hydrogen ions when it loses electrons, and oxygen will gain electrons and produce oxygen ions. Now the hydrogen oxygen fuel cell produces electricity by combining both elements, releasing energy and then water. So here we can see that we have our electrolyte in the center and then our two electrodes, our anode and our cathode at the sides. We then also have chambers where the different gases will be introduced to our fuel cell. So on the one end, hydrogen gas is introduced to our fuel cell, and on the other end, oxygen is introduced to our fuel cell. The hydrogen would be attracted to our anode, and here it will lose electrons. The oxygen would be attracted to our cathode, and here it would gain electrons. This would produce water that would then exit the system. Other unused gases would also exit the system. Now, hydrogen-oxygen fuel cells are becoming more common in the automotive industry to replace petrol or diesel engines. Now, this is because hydrogen can be produced from water, so the process is renewable. They also do not produce any pollution. The only product is water and a little bit of air, whereas petrol engines produce carbon dioxide and oxides of nitrogen that contribute to global warming. Now, fuel cells also release more energy per kilogram than either petrol or diesel, so no power is lost in transmission as there are no moving parts, unlike an internal combustion engine. They are also quieter, so less noise pollution compared to petrol engine. But although they do have a lot of advantages, they do also have some disadvantages. So firstly, hydrogen is obtained by methods that involve combustion of fossil fuels that's then released as carbon dioxide and other pollutants that then contribute to air pollution. And they're also obtained by electrolysis of water that requires large amounts of electricity to produce. The materials that used in producing fuel cells are also expensive, and the hydrogen is more difficult and expensive to store compared to petrol. It's very flammable and easily explodes when under pressure. Now, the fuel cells are also affected by low temperatures, becoming less efficient. And there's only a small number of hydrogen filling stations across the country. And this is talking in terms of America.